All right, a couple things before we begin. In the last lesson, I told you I would look up this question right here when they were both even, and it ended up being extremely, I don't know if aggressive is the right word, but a lot more complicated than it needed to be. So you can trash that question. The ones on your homework and the ones on your exam would be significantly easier than that. You can look at Wolfram Alpha if you really want to see what the answer is supposed to be, and it was an extended response, several terms long. I also wanted to mention, and of course my brain's not working just yet, whatever it is, I'll remember it when it comes, and then we'll get to it. But for right now, we're going to start 8.4, trig substitution. Trig substitution is a lot like U substitution, except you can see that we already have U's. So we're actually transitioning out of a U into a trigonometric function temporarily, and then plugging back in at the end, just like we did with U sub. So before we begin, although this has a radical on it, I want you to ignore that for a second. Which of the trig functions are you most drawn to when you see a squared minus u squared? And I hope that your brain thinks sine, because when we did inverse trig, that was something we were looking for right along. Again, if you ignore the square root sign, then this should draw your attention to tan, and this should draw your attention to secant. And I'm hoping that that will trigger what we're about to work on today. Hopefully that will trigger some of the old information that we've already looked at or worked on. So here's some background. Suppose that sine of theta is equal to u over a. If that's the case, then I can set up a right triangle, and if sine of theta is u over a, then if I have a sine of theta, then the opposite over the hypotenuse would be u and a. If you do the Pythagorean theorem, you would get your second side, your second leg, to be square root of a squared minus u squared. If you don't necessarily want to buy that, you can do it off to the side. Say u squared plus something is equal to a squared. I don't know why I did that. If I subtract u squared from both sides and then take the square root, then b is equivalent to a squared minus u squared. And I'm only going to think about the positive version, because if we're talking about length, then it's not going to be negative anyway. So there's where that third side comes in. Now, what would that third side be equivalent to if you're still using this setup? Well, if I know the adjacent side is square root of a squared minus u squared, then, if I looked at, let's say, cosine of theta here would be square root of a squared minus u squared over a. So if I solved for square root of a squared minus u squared, I could say that it is equivalent to a cosine theta. It's going to be very important. Okay, in order to do this appropriately, you're going to have to know some of these other sub-pieces. They're going to come up when we integrate and so on, and you are going to have to be familiar with identifying each of the different pieces, because we're going to substitute everything out with trigonometric functions. So if I want to rearrange this for u, then u is also equivalent to a sine theta, and then du, the derivative of u, would be equivalent to a cosine theta d theta. At first glance, this might look a little bit overwhelming, but you are going to see it in action here shortly. So just a quick recap. If you have an integrand that involves the square root of a squared minus u squared, and a happens to be a number that's greater than 0, then assign a squared and u squared. Figure out which part of these is going to be equivalent to what. Identify what's going to be your constant, what's going to be your function. That shouldn't be too difficult. U is going to be equivalent, get up here, a sine theta. We're going to balance the integrand accordingly. We're going to integrate, and then we're going to replace. I'm going to do this the long way at first, and then you're going to see where there's some shortcuts that you can take later on. All right, first example. I see a square root with a constant followed by a subtraction of a function. Okay? If that's the case, then 9 is going to be my a squared, and x squared is going to be my u squared. Okay? So just to identify that, get that out of the way. Here's where the actual assigning and figuring out of algebraic details comes in. If I know that this is going to be in the sign category, then I know that u, which by the way is equal to x, right, if I take the square root of both, is going to be equal to a sine theta. That's according to the notes. A would be 3, right? Square root of a squared is 3 sine theta. If you want to write that off to the side, you can. All right, so to go along with this line, I'm also concerned with what du is equal to. Du is equivalent to dx, which I see, and it's also equivalent to the derivative of this, 3 cosine theta d theta. Now I'm going to use all of this stuff that I've figured out and plug it back into the original and see what happens. By the way, this could have been solved using a traditional u substitution, but I want to show you that trig substitution would work as well. All right, x is equivalent to 3 sine theta. Now, if you remember, I can take the square root of a squared minus u squared and substitute it in with a cosine theta, but I'm going to pretend that I don't remember that. And I'm going to plug in direct substitutions here. For example, I'm going to leave 9 alone, and I'm going to replace x squared with 3 sine theta squared. Dx gets replaced with 3 cosine theta d theta. All right, I'm going to clean up just a little bit here. I've got 3 and 3, which makes 9, so I'm actually going to bring that out front. And I'm going to simplify this part of my radicand. I hope you can see that the radicand also includes a common factor of 9, so I'm going to factor that out. And there's a reason behind that. When you take the square root of a product, you can take the square root of the first part and then take the square root of the second part separately. So I am going to square root the 9 right away. And I'm going to leave the square root over this portion, but in an effort to save some time and space, I know that 1 minus sine squared is part of the Pythagorean identity that we've been working with throughout this chapter. So I'm going to replace that with cosine squared. Hopefully you can see why I would do that, because now if I take the square root of a square, and also bringing this 3 out front, I get 27 times the integral of sine theta times cosine theta times cosine theta d theta. You see where I'm going with this? Cosine theta times itself would be cosine squared theta. I'm choosing to put sine theta last because I recognize this as one of the trig integrals from the previous lesson. If this is my u, if cosine is my u, then negative sine is my du. Therefore, this is ready to integrate, and it becomes cosine cubed theta over 3 plus c. Well, if you remember, cosine was not the original value that we had plugged in, right? And also I can simplify this to a 9. Well, how do I get what cosine theta is equal to? Well, it all comes back to the original triangle that this was based out of right from the beginning. Once you get those triangles memorized, then this becomes very easy. But remember, if u is equal to x, and that's equal to 3 sine theta, then I want you to rearrange this and actually think of sine theta. Okay? Sine of theta would be opposite over hypotenuse. The sine of theta would be x divided by 3. Imagine divided by 3 on both sides. So x, 3. And we already know that this combination is going to be that other side. If you didn't know that, you could use the Pythagorean theorem to figure that out. So all I need to do to finish this problem is plug in what the cosine of that theta would actually be. Alright, so now I have negative 9 times the quantity square root of 9 minus x squared over 3, that's cosine, cubed plus c. If you want to simplify it further, which you don't necessarily have to, especially if the answer doesn't say you have to, this is going to become negative 9 rather, times 9 minus x squared. That's to the 1/2, and now with it cubed, it becomes to the 3/2, and then 3 cubed, because we cubed the top and the bottom, is 81. For a final answer, I get negative quantity 9 minus x squared 3/2 over 9 plus c. Now one could argue that this seems like a lot of work for something we could have just done a traditional u sub 4, and you would be correct. But there's a couple places where you can save some time and space. Number one, if you have the fact that this side is going to be your cosine piece, okay, or if you have this part memorized, that takes a lot of the steps out of the process. Also, if you that's exactly what I'm talking about here. So we could have, just right from the beginning, let this part be 3 cosine theta, which would have saved us all 4 of these lines. We could have jumped right to this line. Okay? So keep that in mind. If we're jumping to this line and saving all of this room, that's certainly well worth it. Besides, u sub worked here, but it's not always going to work. Okay? Here's another example where u sub would work, but let's see what happens when we use the trig substitution method. I'm just going to jump to some of the assignings that I know are coming. I know that a, which is the square root of 25, is 5. I know that u, right, if I take the square root of this part, is x. And I also know that if it's a constant that comes before the function x, then this is going to be of the form a sine theta. I also know that I need to figure out the following line with respect to the previous line here. So this is going to be 5 cosine theta. So if by chance you have this all set, but I want you to imagine, because I am going to skip a step here, I want you to imagine that this is replaced with 5 sine theta and we square it. Can you imagine the 25 here and the 25 that shows up from squaring that 5? Can you imagine bringing that 25 out and taking its square root, which would become 5? Can you imagine leaving 1 minus sine squared, which becomes cosine squared, and the square root of that becomes cosine? So if you can walk through that process, then you should be able to identify the denominator as 5 cosine theta. If you can't, then don't. Do all of these steps like we did before. That's fine. X becomes 5 sine theta, and dx becomes 5 cosine theta d theta. So what you're telling me is we're really just taking the integral of 5 sine theta. The answer of 5 sine theta, well, the integral of 5 sine theta would be negative cosine. But remember, cosine is not the original function. We're not using thetas in our original up here. So instead, we need to use the triangle to convert back to what we wanted from the beginning. The triangle is based out of this theta, which is based out of this statement. Just like when we did u sub, our new bounds were based out of this statement. So this is a key player in the whole problem. If I solve this for sine theta, I get x over 5. And I bet if you glance through this page a little bit, you'll know exactly what that second or third side's going to be. It's right there. Again, Pythagorean theorem would work just as well if you didn't trust me or if you didn't want to just accept that. That's fine. All right, so cosine, according to this picture, would be adjacent over hypotenuse, or square root of 25 minus x squared over 5, which means this becomes negative 5 times the square root of 25 minus x squared over 5. Or in other words, negative square root of 25 minus x squared plus c. Okay? A couple things to keep in mind while you're doing this process. Obviously, the assigning of the a's and u's is extremely important. But it's also important whether you do it here, here or at the end. You need the triangle. Both are very important components to this process. All right, keep going. In this case, this would not be a nice u sub. The u on the inside, let me check my focus here. The u on the inside would match, these x squareds are matching, so I know that not only would I have my u sub, but I would have to have a change of variable to plug into this as well, so it would not be as simple. But how would that look for trig sub? In this case, I'm going to do my triangle right from the beginning. I know that a is 4, and I know that u is equal to x. But in this assigning process, since the constant came first, I know it's 4 sine theta. Which means if I solved this for sine theta, it would be x over 4, divided by 4 on both sides. Opposite would be x, hypotenuse would be 4. And this piece right here would be c squared minus b, or a squared. Okay, that's already done, ready to go. I also need to have my derivative line. Derivative of u is du, derivative of x is dx, the derivative of 4 sine theta is 4 cosine theta d theta. At this point, I'm going to go right into the substitution, and I'm going to use the rules right from the beginning. I'm not going to take the long way because I'm limited in my space. dx, if I search for it, is right here. So in trig terms, it's 4 cosine theta d theta. X squared would be x squared, so it would be like 4 sine theta squared. Can you imagine squaring that and put 16 sine squared theta in its spot? I'm also going to walk through this out loud, but I'm not going to write it down in this process. Square root of 16 minus 16 sine squared theta. 16's come out. Square root of 16 is 4. And the square root of 1 minus sine squared is cosine squared, which becomes cosine. All right. Get rid of some repeaters. And I end up having the integral, bring the 1 over 16 out, of 1 over sine squared. Hopefully, you recognize 1 over sine squared by its other name, which is cosecant. And hopefully you've memorized your trig derivatives to remember what this becomes. If you don't, let me remind you with our quick key over here. Again, You may prefer something different, and that's okay. This is just a quick summary. Alright, cosecant squared is this guy. Cosecant becomes cotan, and since there's supposed to be a negative involved, it's going to make this negative turn into a positive. In order to substitute out, you have to be familiar with what cotan is. It is the reciprocal of tan. So if tan is opposite over adjacent, then cotan is adjacent over opposite. In other words, it's the adjacent, square root of 16 minus x squared, over x. Since this does not simplify any better, the only thing I could do is put the 16 with the x. I'm going to leave it as is. Okay, basic trig substitution using sine. So let's move on. We've got tan. Tan was developed with this triangle. If we solve this question or this problem for u, it would become a tan theta. The derivative of that line would be a secant squared theta d theta. And this side over here, right, would be what? Well, I want you to imagine plugging in, and we'll actually show it this time. If I plug in, instead of u squared, I write a tan theta squared. And I should have done this right from the beginning with the last problem. Okay, hopefully that's not too confusing. Well, if you remember, this is part of a trig identity, and it is equal to secant squared theta. And I already told you you can take a product and break it up into two separate radicals. The square root of a squared is a, the square root of secant squared is secant. Okay, so when we encounter the square root of a squared plus u squared, we can already surpass all of the work and just write a secant theta in its place. Okay, let's see it in action. Just a quick reminder, we're going to let u equal a tan theta. We are going to, of course my brain's not working just yet, balance, that makes sense. Balance the integrand accordingly. Then we are going to integrate. And finally, we are going to what the substitute portions. Replace. Replace. Okay. All right. There we go. This could be a u sub, but again, I'm not concerned whether or not it's a u sub. I'm concerned whether or not I can use trig sub in its place. U would be x, which if this is written as an addition problem, then I know that u is a tan theta. And I know that a is 3. I also know that my derivative line is 3 secant squared theta d theta. Now with the substitution. X in the numerator is 3 tan theta. The square root in the denominator, if you remember that piece right from the beginning, sorry, I'm going to do this off to the side as well. Tan is going to be x over 3, and then this side becomes, I'm just going to write it the way that they have it here, x squared plus 9. Okay. We went through the process and already figured this out to be 3 secant theta, but just to run through it quickly, if I plug x squared in with 3 tan theta squared, and I get 9 tan squared theta, the 9's come out, and the square root of 9 becomes 3. I'm left with 1 plus tan squared, and 1 plus tan squared is secant squared. the square root of that part will be secant. And then my dx is going to be replaced with 3 secant squared d theta. You can see a lot of canceling going on, and I'm left with 3 times the integral of, I'm going to rearrange the order, secant theta tan theta. Does that look familiar? Well, if we reference our chart, our derivatives, secant tan is the derivative of secant, which means its integral is secant. Quick substitution, secant would be the reciprocal of cosine. If these are the two sides for cosine, and instead of going adjacent over hypotenuse, we go hypotenuse over adjacent. Hypotenuse is x squared plus 9, adjacent is 3, and this actually simplifies to the radical x squared plus 9 plus c. What do you think? Remember, you can text me at any time if you have any questions, need something to explain further. That's certainly not a problem. Keep going. How do I know that this next one would fall into the tan category? And I hope that your first clue is the plus. Because this has the x in it, we know that this is going to be u. And the square root of this, okay, imagine that it's e to the x to the 4th. I take the square root of it, basically I'm just dividing my exponent by 2. I didn't need to do it that way, that looks weird. Okay, it's just e to the 2x, and it's also 5 tan theta, right? I can do this off to the side. I know that a is equal to 5. My du is the derivative of e to the 2x, which is 2 e to the 2x dx. Okay, this one's a little bit different now. And it's also equal to 5 secant squared theta d theta. Let that sink for a minute. This one was not just a straightforward x dx. You know, we've got something a little bit more complicated. So I'm going to have to look a little bit closer for substitutions. I'm going to pretend that you don't necessarily see them. We're just going to substitute with what we know. E to the 2x. Okay. In fact, e to the 2x dx. See e to the 2x dx? E to the 2x dx. It would be great if there was a 2 there. Well, I can put a 2 and balance it with a 1/2. And now that it says 2 e to the 2x dx, 2 e to the 2x dx, I can substitute it in with 5 secant squared theta d theta. My denominator is the square root portion, which, if you remember, is the a secant theta. But if you didn't remember, again, we're going to walk through it. This would become 5 tan theta squared, which would be 25 tan squared theta. The 25's come out, leaving the 5 when you take the square root. Tan squared theta plus 1 that I'm left with here is substituted with secant squared, whose square root is secant. Question, what is the integral of secant theta? This was one of those that we learned a few chapters ago, chapter 5. We learned how to use, it became a natural log problem, but it was one of those that required a multiplication in the numerator denominator and some manipulation of the integrand itself. I don't expect you to necessarily have this one memorized. It is the natural log of secant u plus tan u. Or in this case, the natural log of secant theta plus tan theta plus c. Well, to figure out what goes in those places instead of secant theta and tan theta, we need to refer to our triangle. Our triangle is based on this statement here. And I know tan, which is opposite over adjacent, is e to the 2x over 5. And I know that the square root portion that I already see up here is the third side. So, for a final statement, secant is hypotenuse over adjacent. Tan is opposite over adjacent. Since they're both over 5, I am going to make one fraction at some point. So secant, again, hypotenuse over adjacent. And tan would be opposite over adjacent. Just to clean it up for my own good, I apologize for this paper moving. Natural log of e to the 4x plus 25 plus e to the 2x all over 5 plus c. You don't have to do that. You also don't need absolute values because e to the 4x will be positive, e to the 2x will be positive, 25 is positive. And no, I cannot put these two together because they have different exponents. Alright, the last portion of your notes is based on what happens when you have the function written first in the difference problem, the subtraction problem. If that's the case, then I rearrange the u here of secant theta, which is going to be my assumption when I have the u first. I get a secant theta. My du would be a secant theta tan theta. And we'll do this like we did the last one. If I replace u with a secant theta, oops, and I do a little algebraic manipulation here, secant squared theta minus 1 is another identity. It brings you, well, same identity that we used before, but solve for something different. It brings you tan squared. Take the square root of both of those, and I get a tan theta. So interestingly enough, when tan is your u, then secant becomes your square root. When secant is your u, then tan becomes your square root. Okay, let's put it into action. Oh, let me rearrange myself here. Okay. Let u be a secant theta. We're going to balance, you remember again, balance the integrand accordingly. Not everybody's going to balance the same exact way, and that's fine as long as it's finally balanced. Then we're going to integrate, and last we're going to replace the substituted portions. Alright. So here's an example of where I would not necessarily want u sub. Yes, my u would probably be 9x squared minus 16, but my du shouldn't be in the denominator. So here's an example of where doing trig isn't going to actually be harmful, but rather help quite a bit. My u is going to be the square root of this portion here, which is 3x, and it's going to be equivalent to a secant theta. Well, a is 4. So 4 secant theta. My du is equal to 3 dx, which is equal to 4 secant theta tan theta d theta. That's a lot. Okay? I'm going to just do this to get it out of the way as well. I know that according to this statement, secant, which is not adjacent over hypotenuse, but rather hypotenuse over adjacent, is equal to 3x over 4. This portion is going to be the square root portion, which we already know is 9x squared minus 16. Again, you can do Pythagorean theorem to figure that out yourself, but it is going to be that, I promise you. My new integrand is going to say square root of 9x squared minus 16, which becomes 16 secant squared minus 16. 16's come out. 4. And then secant squared minus 1 is tan. Then it takes the square root. X, okay, well, here's where it's a little bit different. X is what? Well, I could put a 3 here, and balance it with a 3 here so that it's an actual 3x, that makes for an easy substitution. 4 secant theta. And then I don't have just plain dx, but if I had 3 dx, I could replace 3 dx with 4 secant theta tan theta d theta. Something else you could do is, if you didn't want to do it this way, you could divide both of these by 3 and replace dx with 4/3 secant tan theta tan theta d theta. So that's certainly an option. Alright, when all is said and done, I have 4 times the integral of tan squared theta d theta. That's not a traditional trig sum. Instead, it falls into the category of what we learned in 8.3. And we learned in 8.3 that if you have an even square, like if you have an even powered tan function and it's the only function you have, use the identity to get rid of it. So tan squared is equal to secant squared theta minus 1. And hopefully you can see the two separate integrals here, secant squared theta d theta minus 1 d theta, as being actually quite simple. The integral of secant squared is tan, and the integral of 1 d theta. Alright, so this brings us into a territory that we haven't encountered just yet. We haven't had theta by itself. We'll get to that piece in a minute, but first, let's substitute out tan. Tan, according to this triangle, would be opposite over adjacent. Square root of 9x squared minus 16 over 4. Now, how do I figure out theta? Well, if you remember, this statement right here is the most important piece of this entire puzzle. Since x was my original variable, I'm going to focus on just that portion. Here's a little key off to the side. Okay. 3x is equal to 4 secant theta. Solve for theta. So 3x over 4 is equal to secant theta. Again, solve for theta. If you take the inverse secant of both sides, then arc secant of 3x over 4 is equal to theta. Okay, unraveling that gives me arc secant 3x over 4 plus. You could go through, multiply that 4. It would cancel with the first 4. It would not cancel with this one because that's inside the argument, inside the angle. But since it's not going to simplify both terms, I'm just going to leave it on the outside. It's no big deal. All right, a couple more. In this case, it's a positive, so which one are we going to use? Hopefully you remember tan, so A, tan theta, oops, I didn't want that. It's going to be A, tan theta, du is equal to dx, which is equal to 1 secant squared theta. No, we don't need the ones, but I wanted to write them down either way. So this is equivalent to dx, which is secant squared theta d theta, over, well, this is non-traditional because it's raised to a power other than just a 1/2. So I'm going to actually do direct substitution here. I'm going to put tan theta, I'm going to square it, plus 1. And raise it. I know that tan squared theta plus 1 is equal to secant squared theta. And I hope you realize that if this is squared and I'm taking a square root, the only power left is going to be that cube. Again, let me explain that one more time. 2 times 3 halves is going to turn out to just be the 3. Okay? Which means that I have the integral of 1 over secant theta. But secant theta is the reciprocal of cosine, so if I do its reciprocal, I'm just taking the integral of cosine. Which means I just have sine. Substitute that out, and opposite over adjacent, or x and 1, so becomes x squared plus 1, and my final answer is going to be opposite over hypotenuse. There we go. How does this concept work for definite integrals? Well, we've gotten into the habit of when we substitute out our angle never going back, or substitute out our bounds never going back, and I'm going to keep that true here as well. In this case, I know that a is equal to the square root of 3. I know that u is equal to x, and since it's the u part first, it's equal to the square root of 3 secant theta. I also know that du is equal to dx, which is equal to square root of 3 secant theta tan theta d theta. I also know that when I do my u bounds, when I do my substitution bounds, I go out of this very important statement that I've mentioned before, it being the most important piece of the puzzle. If these are x values, then what happens when I plug in square root of 3 in for x over here? What do I get? We'll come back to that because I do want to focus on the actual process here of substituting out first. So let's see. Square root portion of a secant is going to be a tan. X, square root of 3 secant, and dx is square root of 3 secant theta tan theta d theta. Okay. So, if I plug these in for x, being x values, then what are my new theta values going to be? Okay, I'm going to do this off to the side so you can see it in action. If 2 is equal to x, then what is going to be the value of secant, or what's going to be the value of theta? We mentioned already that secant is the reciprocal of cosine, so if I change this, then I can change this, and I know that cosine theta is the square root of 3 over 2 at what point? Well, it doesn't hurt to have the reminders. And I'm not going to fill it all in because I already know what's going to happen here. So if sine moves up and cosine moves down, then this is 0, 1, 2, 3. This is the one I'm going to use, 30 degrees. It's not kosher to use 30 degrees, but rather pi over 6. So instead of 2, I'm going to write pi over 6. Instead of root 3, this becomes 1 equaling secant theta, and the reciprocal of that is still going to be 1. And if I go back to this chart, cosine is equal to 1 right here. Again, if you work your way up to 1 in sine, then you're working your way down to 1. So there's going to be 0. Okay. So now I've got the integral, root 3 brought out, of tan squared theta d theta from 0 to pi over 6. We already did tan squared theta. Yep, it was a couple portions ago. And the integral of it, if you remember, this was secant squared minus 1. Secant became tan. I'm going to skip a step and I'm just going to say refer to, how many slides ago? 1, 2 slides ago. Now here's where you have to really be paying attention. Oh, I'm sorry, that's supposed to be a minus. Okay. You do not have to substitute this in with arc sine or arc secant of anything. These are now answers in theta, and I found my new bounds in theta. If you don't feel comfortable with this, then you can leave the bounds off right from the beginning, go back and substitute at the very end, and use your traditional bounds. But I'm going to stop here with these bounds. And I'm going to type in or figure out tan of, whoops, not going to read pi over 6 minus pi over 6 minus tan of 0 minus 0. Alright, pi over 6 is 30 degrees, tan is sine over cosine, so at 30 degrees, this is root 1 over 2, this is root 3 over 2, so it's 1 over root 3. There's a lot of work going on here to rationalize that, so this becomes root 3 over 3. Tan of 0, that should have been a 0. The sine value is 0, so this is going to be 0. Alright, running out of room, so I get square root of 3. I'm going to combine these. I'm going to make that a 6 in the bottom. So it becomes 2 root 3 minus pi over 6. I can bring the root 3 in if I choose. I guess it will make it better. This will become 6 minus root or pi root 3 over 6. And if you want to simplify it further, again, I'm going a little crazy here, but you know, off the top of my head, I don't know if that was the right answer. I certainly don't ever settle on definite integrals. I always check with my calculator. All right, if I'm going to do the integral from root 3 to 2 of the square root of x squared minus 3 over x equaling dx. This is the answer I get as a decimal. My final answer was 1 minus the fraction pi root 3 over 6. Came out to be the same answer. Now I realize that there's some discrepancy here, but that's simply because of, you know, calculation errors. This is not taking an exact integral. It's using something like a series of answers, or, you know, we talked before about trapezoidal rule or Simpson's rule, things like that. So there might be some rounding errors. Plus pi is an infinite irrational number. There could be some errors figuring things out, but either way, that was close enough in my opinion. All right, to wrap this up, we're talking about special integration formulas. They were given in front of you, and it says find the arc length of the graph. Now this is going way back to chapter 7. Now it wouldn't seem way back since we're in chapter 8, but we did chapter 7 in Calc 1. And arc length was equal to the square root of 1 plus the function's derivative squared dx. Do you remember that? That means that it is equivalent to, in this case, the square root of the function, not square root, the derivative of the function would be 2 times 1/2, which is 1. It would be just x. Alright, so now this says 1 plus x squared. That means I have a plus sign. I'm thinking, got my integrals, I'm thinking tan. A is 1, U is x, which is A tan theta. du is dx, which is secant squared theta d theta. Quick substitution. My integral in a tan formula is the secant. Dx is equal to secant squared theta d theta. And what do I do when integrating secant cubed theta d theta? Do you know? Well, I am going to actually go back a step, and I am going to change secant squared into tan squared theta plus 1. Alright, so this becomes secant theta times, now bear with me, tan squared is equivalent to, oh, I don't want to do that. Okay, let me think here. Secant cubed. I'm going to reference my notes and go back to 8.3, and it tells me what to do when I have an odd secant. Okay, it doesn't mention that. It mentions if you have an even secant, saving 2 secants, I'm on this page right here, rules for integrating. It mentions if you have an odd tan, and it mentions what you do if you have all tan. So let's brainstorm. Secant cubed would be secant tan squared tan Alright, just like before, instead of wasting time, I'm going to star this, I'm going to go do it on my own and come back to you with a final answer. A little bit of a longer lesson, but I hope you understood all of it. If you don't, come back to me, text, you know the drill.